In this video, we're going to explore composite functions. We'll start by exploring what are composite functions, and then we're going to discuss some of the quirks around the domain and range of composite functions. And throughout our discussion, we're going to discuss some of the ways in which these concepts are tested in your exam. Let's get into it. Before we get into composite functions, let's quickly review functions. A function typically takes the form f of x, where f is the name of the function and x is the input variable to that function. A composite function is a function whose input is yet another function. Suppose we have two functions f of x and g of x. These two functions can create two unique composite functions. The first is f of g of x. The idea here is that we're going to go through f of x, and everywhere that we see x, we're going to replace with g of x. Once we do that, we typically simplify the result. The other composite function that we can create is g of f of x. The same concept applies here. We're going to go through g of x, and everywhere that we see x, we're going to replace with f of x. And again, we'll simplify this result. It's worth mentioning that f of g of x is not the same thing as g of f of x. So pay close attention to what composite function you're actually supposed to be finding in your exam. And just a quick note on notation, there's a couple of different ways in which composite functions can be expressed. The first and most common way is the way that I've already expressed it, where you have f of x on the outside and g of x on the inside. Another way you could express it is fog all of x, where f is the outer function, g is the inner function, and x is the input variable to the whole function. There are a few rules when it comes to composite functions. The main one is that the range of the input function must be a subset of the domain of the output function. What does that mean? Well, let's look at how composite functions actually work under the hood. Suppose we want to find f of g of x. When you break it down, here's what this actually looks like. You start with your input variable x, and you feed that into g of x. G of x is its own unique function, which produces some output. That output is then fed back into f of x. And finally, the output of f of x is your final result. Here's the catch. F of x and g of x have their own unique domains and ranges. If the range of g of x is too big or too small to fit in the domain of f of x, then the function will be undefined because it is outside of the domain. To illustrate this, let's use the functions from before, but this time we're going to restrict the domains. G of x is a strictly increasing function. This means that as the input x gets larger, so does the output y. Hence, the range of g of x is found by substituting in the lower and upper bound of the domain, giving us a range of 0 to 9. The range of g of x is greater than the domain of f of x, and for this reason, the composite function is undefined. For example, we can substitute 3 into g of x and get a result of 9, but we can't go ahead and then feed 9 into f of x because it falls outside of its domain. And it's for this reason that the composite function is considered undefined. Here's an example from the 2023 Tech Active exam that tested this concept. We are asked to find the largest interval of x values such that both composite functions are defined. Well, we know that any composite function exists as long as the range of the input function fits in the domain of the output function, so a good place to start is to figure out what are these domains. The good news is we're already given the domain of g of x. Now we just need to find the domain of f of x. The domain of any logarithm can be found by grabbing its input and then finding where that input is greater than 0. This is because any logarithm will be undefined if it has a negative or 0 input. And when we solve this inequality, we're going to get the result x is greater than -1 on root 2. Now that we know the domain of each of these functions, this tells us the maximum allowable range of each of the inner functions. Again, this is because each function needs to be able to fit inside the other one, and it can't do that if its range of output values is greater than the outer function's input values. But remember, the range of the function is dictated by its domain. So, now that we know what range we're after, we now need to work backwards to figure out what domain gives us that range. Starting with f of g of x, we know that the range of g of x must fit in the domain of f of x. So, what we're going to do is set the range of g of x to be the domain of f of x, and that is x is greater than -1 on root 2. And then, we're going to solve all the possible x values of g of x that fit into that range. This question is tech active, so feel free to use your CAS to solve this. Just don't forget to let the CAS know that g of x has a restricted domain. This result is a little bit weird, so let's explore it. The min on the right hand side just tells us that our upper bound is going to be the minimum value of either 5 or 5 pi on 4 plus 2 pi n, whichever one of those is smaller. For example, if n was 0, then the 2 pi n terms would just disappear, leaving us with 5 pi on 4 on the right hand side. 5 pi on 4 is less than 5, hence our upper bound becomes 5 pi on 4. The CAS is doing this because it doesn't know what value of n you're interested in. N could be 50, in which case the general solution 5 pi on 4 plus 2 pi 50 would be much larger than 5. So your upper bound would become 5, because again, it's the minimum of these two values. Now that we know the domain of f of g of x, we can now do the same thing for g of f of x. We know that the range of f of x must fit in the domain of g of x, so we're going to say that the range of f is going to be equal to the range of g of x. And again, we can use our CAS to solve this. So far, we found the domain of each individual composite function. But what we want to know is the domain such that both composite functions are defined. And to do that, we need to find the intersection of both domains. If we plot both intervals on a number line and only look at the intersection, we see that our new interval is from negative root 2 on 2 to 5 pi on 4. But that's not one of our multi-choice answers. So what's going on here? There's one final trick here, and it has to do with how square roots are represented. If we multiply the top and bottom of negative root 2 on 2 by root 2, then the fraction becomes negative 2 on 2 root 2, which simplifies to negative 1 on root 2. Thus, our final answer is A. Why not B? Well, it comes down to our inequalities. Notice how these are all non-inclusive? This means that the domain must also be non-inclusive. Thus, we're only going to use open brackets like in A. The most common applications of composite functions come alongside calculus-style questions or alongside circular functions. Oddly enough, for this example here, you won't need to know any calculus fundamentals. You just need to understand that f of x and f dash of x are two separate functions. This one here that we're going to go through came from the 2022 Tech Active exam. Let's give it a shot. First, we're told that g of x is a composite function f of sine 2x. But we aren't told what f of x is. Instead, we're given this table of known values that links specific values of x to the functions f of x and f dash of x. The first part is simply asking us to find what is g of pi on 6. Now, the rules of functions haven't changed. Whenever we want to evaluate a function at a specific x value, we're going to go through that function, and everywhere that we see x, we're going to replace with that value, which in this case is pi on 6. Once we simplify, we see that we're left with f of sine pi on 3. We can simplify this further by evaluating sine pi on 3. Consulting the unit circle, we can see that sine pi on 3 is root 3 on 2. If you aren't familiar with how to solve circular functions like this, check the link above for an in-depth walkthrough. I'll even leave a link in the description as well. For now, we've simplified our expression down to just f of root 3 on 2. This is where the table of known values comes in. We know that if x equals root 3 on 2, which it does, then f of x at that value will be 3. Hence, we can replace that entire expression with just the value 3. So finally, we have our answer. G of pi on 6 is just 3. We can apply this exact same process to part B. Again, don't worry about what the derivative is, this is just a calculus term, and we'll cover that in a later video. For now, just know that g dash of x and f dash of x are their own unique functions. Once you understand that, part B isn't much different to part A. It's even got the same input variable. It's just that the function is a little bit bigger. So, just like in part A, we're going to start with our initial expression and slowly simplify things as we go forward. Like before, we'll start by subbing in pi on 6 and then simplifying these results. We already know from before that sine pi on 3 is just root 3 on 2. And when we consult our table of values, we can see that f dash of root 3 on 2 is just 1 on 9. Now all that's left is to evaluate cos pi on 3. Again, consulting the unit circle, we can see that cos pi on 3 is just a half. Now all we've got to do is sub this back into our equation and simplify. And sure enough, we get our expected result of 1 on 9. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.